Okay, let's begin section 5.2, which is on free and undamped motion. This is actually a fairly straightforward section, but it gives us a baseline from which to build the case for what happens when you put friction into the system. So when we take friction out of our general equation, we just get mx double prime plus kx equals 0. Traditionally, you divide through by the m and then define lambda to be the square root of k over m. That gives us x double prime plus lambda squared x equals 0. So our characteristic equation, m squared plus lambda squared equals 0, and m is plus or minus lambda. Okay, that makes writing down our solution fairly straightforward. X of t is going to be a sine of lambda x, plus b cosine of lambda x. Okay, and that makes sense. You would just get a nice oscillating function. Now, again, sometimes we want to write this in a different form because we want to talk about the period and the amplitude of these waves and so on. So we do a strange thing. Now, you can actually find formulas for A and B if your initial conditions are given at 0. I like to just leave them as constants that we'll solve for along the way. Notice this is not an undetermined coefficient system. I'm just using A and B for convenient constants. So I'm going to rewrite this as the square root of a squared plus b squared times a over root a squared plus b squared times sine of lambda x plus b over square root of a squared plus b squared cosine of lambda x. That's sort of a strange thing to do. But the thing to notice is if we look at the vector opposite of A, let me see here. Let me scratch that. We want to take the B over root A squared plus B squared. And then put opposite of A over square root of A squared plus B squared. So that's going to be our vector. We get the norm of V. Its distance is 1. In other words, this ordered pair lies on the unit circle. So there exists some angle, phi, such that cosine of phi is our b over square root of a squared plus b squared, and sine of phi is our opposite of a over a squared plus b squared. Because any point on the unit circle has an angle associated with it, and the cosine of that angle is going to be the x-coordinate, and the sine of the angle is going to be the y-coordinate. And so we get this new equation, let me start a new paper here, that we can write x of t is negative sine of phi sine of lambda t plus cosine phi cosine of lambda t. And that whole thing we still are multiplying by root a squared plus b squared. Okay, now that looks like it's not a whole lot better until we realize that this thing is actually an angle addition formula. The cosine of an angle theta 1 plus theta 2 is cosine, cosine, minus sine, sine. So that's actually the angle addition formula for cosine. So x of t, we're going to get our root a squared plus b squared. And then we're going to get cosine lambda t plus phi. Okay, I like that because it tells me something about the motion. My amplitude, so in sound, of course, amplitude would be the volume. Amplitude is going to be square root of a squared plus b squared. So that's going to be the amplitude of the motion. Notice, even though it looks like we had two trig functions going at once, actually it reduces to one. Now, the t is going to cycle it through. Now, to get from one peak to the next peak, we have to get lambda t to go from 0 to 2 pi. So my period is going to be 2 pi over lambda. The frequency is simply the reciprocal. So you can see if we make lambda bigger, notice lambda is root k over m. So to make lambda bigger, we would need a stiffer spring or a lighter mass. Okay, so that would make the frequency go up to make lambda bigger. So notice, to make the frequency go up, we have to have a higher k. So think about piano tuning. If I tighten the string, that makes it stiffer, so the k goes up, so the note goes up. Same on the guitar. If I take a thinner string, then I decrease the mass, which again makes lambda go up. And so you'll notice that the high notes tend to be the thinner strings, the low notes tend to be the thicker strings. And then you tune them by tightening or loosening them, which affects the spring constant. Now, it's not a true spring, but the same basic idea. It's a restoring force. Okay, so we have period, we have our frequency. This phi over here, well, if you take cosine t, lambda t plus phi, you can write it as, let me see here, we want to do one cycle, so cosine of lambda times t plus phi over lambda. It's sort of a strange thing. This phi over lambda is called the phase shift. And it's simply, okay, where in the cycle do you begin the thing? So this is a cosine curve, but you start halfway through the curve or a quarter of the way through the curve. So when you hear the term phase shift, it's really talking about that angle over lambda as to how far out of sync it is. That one we're not going to worry about too much. We are worried about, though, the period and the frequency. The nice thing with this is, in this section, since there's no friction, once you start this thing going, it's always going to be the same. So you're going to have this amplitude, this period, generally use period when you're talking about something longer in duration, something higher frequency where you have maybe a rapid oscillation. That's when we use frequency to describe it. It's simply the reciprocal of the period. And then we will look at what happens to these quantities when we start adding friction in. And it makes sense that at first, if you add a little bit of friction in, it's going to change the period and frequency a little. It's going to change the amplitude a little bit because the thing's not going to want to stay going. It's going to slow down over time. Eventually, you're going to get to the point where there's so much friction that it just won't oscillate. If you put a spring in molasses, it's not going to oscillate. Okay, so we want to talk about, okay, what are the conditions necessary for oscillation to occur, and how does adding friction into the system change all of this? Okay, so that's the end of section 5.2. Stand by for section 5.3.